Well, thanks to the conference organizers and the session chairs for giving me the opportunity to talk today about some of my thesis work. So some motivating questions for this talk are: how do stars of different mass and composition evolve? How does this impact the location of a habitable zone around a star? How does the habitable zone co-evolve with the star over time? And how will utilizing this knowledge apply in the continued search for potentially habitable Earth-like planets in the future? So I know I don't need to belabor the point that habitable zones are complicated concepts, but I just want to emphasize that for the context of this work, we're approaching habitability or the habitable zone from the astrophysical perspective in terms of thinking about how stars of different mass and temperature, how their habitable zones differ. And also make the point that for different mass stars, not only are the distances of the habitable zones variable, but they expand outward at different rates. So the two main measurable parameters that I look at are mass, which impacts the rate of hydrogen fusion in the star, which thus impacts the main sequence lifetime of the star, as well as the composition, which affects the opacity, energy transport within the star. So something with a star with lower opacity, for example, would have more efficient energy escape and a shorter main sequence lifetime than a star of equal mass. So what I do to model stellar evolution is I use Tycho, a one-dimensional hydrodynamical code, which outputs stellar surface quantities of interest for each time step of the evolution. So typically temperature and luminosity are what we're primarily interested in. And I've created an online database for the evolutionary tracks that's available. It has an interactive interpolation tool as well. And primarily what we want from these evolutionary tracks is to look at how the location and lifetime of the habitable zone depends on the changes over the star's main sequence lifetime as it goes. So looking at the temperature and luminosity, we have the HR diagram. Even just for looking at oxygen, if we have depleted oxygen dashed, enriched oxygen compared to the sun in dots, you can see that there's quite a significant spread in the temperature and luminosity outputs for the HR diagrams for each mass in our range. And if we plot the sun on our tracks, we can see that this is a good estimate of the current sun temperature and luminosity. So just believable estimates for what we're getting here. So the limit equations that we use also come from Ravi Kaparapu's 2013-2014 papers. What we're focused on here, again, the temperature and luminosity. So we take that from Tycho and input this into these equations that calculate the habitable zone distance at each time step in our evolution. And this is the program that I wrote to do these radii calculations are easily upgradable for any particular habitable zone prescriptions that you want to use. But we chose the conservative cases from Kaparapu, which are the runaway greenhouse and the maximum greenhouse cases. And that's where total ocean evaporation to the point at which Rayleigh scattering by CO2 starts to outweigh the greenhouse effect on the outer edge. So with elemental abundances, what we're thinking about is that usually only iron is measured in stars because it's easy, there are lots of lines, and other elements are just assumed to scale in the same proportions that are observed in the sun. But as in Natalie Hinkle's 2014 paper especially, we see that specific chemical abundances can vary significantly among stars. And also previous work by Patrick Young has shown that oxygen specifically has a really strong impact to the stellar evolution. So my database that I put together for the stellar evolution tracks, in 2015 paper I discussed a grid of 376 models that range from 0.5 to 1.2 solar masses. It has a scaled overall metallicity relative to the sun, so just scaling all the elements proportionally from 0.1 to 1.5 solar metallicity, and then a specific oxygen abundance values ranging from 0.44 to 2.28 solar oxygen. And in my recent paper, we added an additional 528 models. So that's for carbon, magnesium, and neon. And neon's an artificial range here, just because it's very difficult to accurately measure in stars, but we want to include it, even hypothetically, because it's important for considerations into the stellar evolution. So what we're plotting here is habitable zone distance versus stellar age. So we have age and distance, and we have the inner limits and the outer limits here. Each color represents a different elemental abundance. So we have oxygen in red and purple. You can see that they make the most difference versus the black line, which is solar. Then orange and blue are magnesium, and yellow and green are carbon. And interestingly, carbon actually makes less of a difference than magnesium, even though it's relatively more abundant in stars. But magnesium has a higher opacity per gram, so it impacts the difference in the evolution, the temperature and luminosity outputs. And not only do the habitable zone distances differ with variable composition, we also see that the lifetimes, again, can be significantly truncated. For example, if we're looking at depleted oxygen here versus enriched oxygen, there's a difference of maybe 3 billion years. So it's quite a big difference. If we plot the Earth here, you can see that Earth is on the inner edge of the habitable zone currently. However, if we're thinking about some sort of hypothetical exoplanet at the same current time, then you can see that it's only recently entered the habitable zone. So up until this point, it's been what we would maybe consider outside, and we don't know now what implications that would have for this planet. So generally, though, we want to avoid planets that have only recently entered the habitable zone. This table is showing the fraction of orbital radii that do enter after the midpoint. And what I want to highlight is that up to a third to a half of all orbits in the habitable zone only become so in the second half of the star's main sequence lifetime. And additionally, a trend that we see is that with increasing composition, a higher percentage of planets are not in the habitable zone until the second half of the star's main sequence lifetime. So this prompts us to constrain with a time criteria our consideration of the habitable zones. So I wanted to show this. It's kind of a complicated figure, but mostly what we're looking at is distance here versus stellar mass. And this is for all of the 376 grid. It just basically is meant to illustrate that we see a wide range of habitable zone distances based on the stellar composition. So it can really impact what we're seeing in terms of distance based on the wide variety of stellar compositions we have. Okay, so if we pick out one, which is just the solar value, and we look at what we would think of as a continuously habitable zone, the green shaded region here is what we would think of as the CHZ1, which is the where something would be continuously habitable for the star's entire main sequence lifetime. So you see that that's not a very comprehensive way to think about it, because if we plot Earth on here, that doesn't find Earth. So we know that Earth is in what we would consider the habitable zone, so we need to be more careful about how we define this continuously habitable zone. Instead, if we use a 2 billion year criteria, which is based on, obviously, Earth took about 2 billion years to produce enough biogenic gases that would be detectable with something in the most recent decadal survey. Then we have that Earth does fall into this range of orbits that would be continuously habitable for at least 2 billion years. So anything within this green range would meet that criteria. Now here's a table illustrating that, and what I want to draw the attention to here is that for low mass stars, obviously they have a very high percent of time that a planet would spend in the 2 billion year continuously habitable zone versus the entire main sequence, whereas something with lower composition at higher mass don't have any orbits that are continuously habitable for 2 billion years. just because of the short main sequence lifetime. So that could help us constrain maybe the types of stars we want to focus on. As well, we can provide accurate time evolution of a wide array of stars to better evaluate individual cases of interest as they arise. So the current work that I've been doing is expanding the catalog to also include a grid of M-dwarf stars, which utilize the same range of abundances for oxygen, carbon, magnesium, et cetera, except for now we have from 0.1 to 0.45 solar masses to hopefully incorporate all the interest for M-dwarf habitability. And I'm also writing a Tycho subroutine that will be able to estimate the activity versus age for each star in our catalog. This is based on a minimalist couple evolution model from Blackman and Owen 2016. And I'm also working on keeping the database updated. It's designed for the astrobiology exoplanet communities to basically characterize any particular system that we're interested in, any new discoveries that are coming up, planetary candidates, so we can look at the host star characterization and try to get an idea of what's going on with that. So with that, I will stop and I'll take questions if there are any.
Questions for Amanda? Sunny?
So Amanda, this is really cool. And I was curious if you had, so you said you were going to these smaller stars, and I was curious if you had any intuition as to what the, essentially you start forming molecular species in their atmospheres and what that might say for your stellar effective temperatures and luminosities.
I think that would, I mean, it's just generally lower, but are you
Right.
saying like
Well,
different species could impact differently?
Right. So is that going to affect your luminosities at all?
I think, yeah, it definitely will, but I'm not sure I can say anything about specific species, like how particular molecules might affect. But
Right.
I think absolutely that, yes, having that and at the lower effective temperatures will impact the stellar evolution.
Okay.
But I'm not exactly sure because I don't know how each specific species will interact in the whole process. So.
Cool. Thanks.
I guess the idea that I've heard around that is that by increasing the amount of absorption towards the red, you effectively widen the Hab zone a little further out, and that especially around M dwarfs, where the light is redder.
Right.
And planetary albedo is smaller at those wavelengths. I guess that I was thinking about, the minimum age or the minimum continuously habitable time, in terms of setting constraints on which types of stars could have habitable planets around them.
Yeah,
and,
for
it'd
sure.
be fun to, we've thought about this, a lot, but it would be fun to translate, what if you want planets that are at least 1 billion years habitable or 2 billion into actual mission detection parameters, because planets in the habitable zones around A stars, for example, have a much steeper contrast rate that you have to reach then to detect those than in the Hab zone around a G star or a
Right.
K star, an M star. But then also they're further out, so it's a little easier in terms of inner working angle. But it would be fun to actually try to map that out in terms of contrast inner working angle, as well as the actual apparent magnitude of the planet that
Yeah.
you'd have to get down to for specific stars.
Yeah, that's really interesting. I've had discussions about kind of doing contour type plots even with like different ages or different time criteria. So like 1 billion years or 2 or 5 or whatever. So that's also
Yeah.
really interesting.
At the end
point,
of the day,
so.
you kind of have to do it star by star, so it's
Right.
super time consuming, but it has to be done.
Right, yeah.
All right, let's thank Amanda again.